In 14-2, students will be able to understand and explain the following: areas of rectangles, parallelograms, triangles, kites, trapezoids, regular polygons, circles, and sectors of circles. Conversion of area units. Ratio of area measures of similar figures. Let's consider this geoboard, which consists of the following figure on the right. We're going to use the addition method and divide an area into smaller pieces and then add the areas. What is the area of this figure? Well, first we'll start and divide it into simple figures like rectangles and triangles. And here I have divided the area into rectangles and triangles, and we'll be able to calculate the area of each figure. This area for this large rectangle is a 2 by 3, so we have 6 square units for this rectangle. This triangle is half of a square unit, so we'll put 1/2. And for this long rectangle, it is a 1 by 4, so this is 4 square units in area. This rectangle has 2 square units in area. And this square is a 2 by 2, so we have 4 square units for that one. And each of these small triangles has an area of 1/2. This small square has an area of 1 square unit. So all I have to do now to find the area of this figure is to add up all of the areas. If I add up all the areas, we have 6 plus 4 plus 4 plus 2 plus 1 plus there are 1, 2, 3, 4 1/2. So we're going to add up this expression and we get 19 square units. So the area of this figure is 19 square units. For the rectangle method, we're going to construct a rectangle encompassing the entire figure, then subtract the areas of the unshaded region. In this figure, it is very difficult to break it into rectangles and triangles because the dots don't line up with all of the sides. So what we're going to do instead is construct a larger figure around this in the shape of a rectangle. From there, we can break up the figure into different shapes. We have shape A, B, C, D, E here that are not part of the area that I want. Now I can calculate the area of the entire rectangle, which is a 4 by 4. So we know there's 16 square units for the entire rectangle, but that is too big. We want to subtract the area for A, B, C, D, and E. The area of figure A is 1/2 that of this rectangle. I know this rectangle is a 2 by 3, so I know this total area is 6. But the figure A is half of that, so this must have an area of 3 square units. Similarly, this rectangle is double that of area B. So I'm going to take this area, which is a 1 by 2, and cut it in half, and that gives me an area of 1. So B here has an area of 1 square unit. D has an area of 1 square unit because it's a 1 by 1. E is similar to B because it's half of a 1 by 2, so E has an area of 1. C is also the same idea, so we have this is an area of 1. So to find the area of the shaded region, we will take 16 and subtract 1 plus 1 plus 1 plus 1 plus 3, and this gives us an area of 9 square units. Let's look at another example, and we want to find the area of this shaded figure. We're going to start by the same process. Let's break it up and draw a rectangle around the boundary of this figure. And as you can see, the figure now has a rectangle around it. And now we'll start to break this figure up into rectangles and triangles. So here I can break it up into a square, and these will become triangles. And I could drop down a line here, and this becomes a triangle. I'll break up this into a triangle and a square. The areas of the hexagon equals the area of the surrounding rectangles minus the sum of the figures A, B, C, D, E, F, and G, which we found earlier. We know the area of the hexagon equals the area of the surrounding rectangle minus the sum of the areas of the figures A, B, C, D, E, F, and G, which we broke up earlier. So now I know the area of this big rectangle. It is 3 times 4, so the area is 12 square units. We know the area of the big rectangle is 12 square units. Now to find the area of A, I'm going to construct a rectangle here, and this rectangle has an area of 3. This rectangle here has an area of 6 because it's a 2 by 3. So I know the area for A must be half of that, since it's half of the rectangle, so the area must be 3 square units. For B, it's just a 1 by 1, so we know the area is 1. C, we know that's half of a 1 by 1, so the area is 1/2. And similarly, D is the same, so D has an area of 1/2. For E, it is half of a 1 by 2, so I know the area of E is 1 square unit. F is a 1 by 1, so we know the area is 1. G is half of this rectangle, a 2 by 1, so G has an area of 1 as well. So we have the area of our shaded region is equal to 12 minus 1 plus 1 plus 1 plus 1 plus 1/2 plus 1/2 plus 3. So we're just taking the area of the big rectangle and minusing the area of the parts we don't want. This will give us an area of 4 square units. Here is a table that shows you the relationship between the square meter, which is our base unit, and the square units of other areas. Now this table is not commonly used. I will use instead another table to convert metric units of area. This is the chart I'm going to use when I'm converting metric units, and we have seen this chart already from a previous lecture. This is equivalent to moving 3 decimal places to the right, so the decimal point for our 5 meters is on the right side here. So this is equivalent to 1, 2, 3 spaces to the right, so that is 5,000 millimeters. So 5 meters is equivalent to 5,000 millimeters. Let's say I want to convert from 150 centimeters to kilometers. In order to do this, we're going to use the chart again. So I'm starting from centimeter here, and I'm going to move 1, 2, 3, 4, 5 places to the left here to get to kilometers. So I'm going to move the decimal place here, 5 places to the left. 1, 2, 3, 4, 5, and this is our new decimal point. So 150 centimeters is equivalent to 0 point, and I need 1, 2 zeros here, 1, 2, and it is this much kilometers. So 150 centimeters is equivalent to 0.00150 kilometers. So this is a quick review of what we have already done in the previous lecture. Now let's try to convert 5 centimeters squared to millimeters squared. Now the key feature here is these are square units, so we cannot use the same process we had earlier. So be careful. We're going to start with 5 centimeters squared, and we're going to multiply that by a unit fraction. Remember, unit fractions are equal to 1. Unit fractions have a value of 1, so they don't change the expression. I want to multiply 5 centimeters squared by a unit fraction here. I want to cancel out the centimeters, so I'll place it down here. Now I want to cancel out centimeters squared, but this is just centimeters, so we're going to have to square the top and bottom of this fraction. Now I know 1 centimeter is equivalent to 10 millimeters. Now how do I know that? I can go back and look at my chart. We're converting from centimeters to millimeters, so I move the decimal place 1 time to the right. So 1 centimeter is equivalent to 10 millimeters. So that is going to be used to do our conversion. Now remember, we need square units here, so I'm going to square this entire expression. And squaring a number that's equivalent to 1 doesn't change anything, so it's okay to do. So this is equivalent to 5 centimeters squared times now 100 millimeters squared, because 10 squared is 100. And on the bottom, 1 centimeter squared is going to give us 1 centimeter squared. Now notice the units are the same now, and then they can finally cancel out. So we have 5 centimeters squared is actually equivalent to 5 times 100 millimeters squared. So that is equivalent to 500 millimeters squared. So that is our conversion. So please don't make the mistake of moving it 1 decimal place to the right and saying it's equivalent to 50 centimeters squared. It is not, because we have to square at some point when we want to cancel out the centimeters squared. So be careful in that regard. Part B, I want to convert 124 million square meters to square kilometers. So we'll start with 124 million square meters first, and I want to multiply it by a unit fraction. Now it's really hard to use meters squared, so we'll start with meters first. Let's put 1 meter on the bottom, and then we'll convert 1 meter into kilometers here on the top. So let's go to our chart. So 1 meter is equivalent to how many kilometers? We'll start with our base unit, and we'll move it until we reach kilometers. 1, 2, 3. So we need to move our decimal place 3 times to the left. So we'll start here and move it once, twice, 3 times to the left. So we get this is equivalent to 0. This is our decimal place, 0.001 kilometers. So I know 1 meter is equivalent to 0.001 kilometers. So 1 meter on the bottom, since we want to cancel out the meters, and 0.001 kilometers on the top. Again, this is meters squared, so we need to square the top and the bottom, which is okay to do, again, because this has a value of 1. It doesn't change anything. So we can square the top and the bottom, and this gives us 124 million square meters times, we're going to simplify the right here, 0.001 squared is equivalent to 0.00000. There should be a total of 5 zeros here and a 1 kilometer squared on the top. Now in the denominator, 1 meter squared is just 1 square meter. So we have our unit fraction here. Notice the meters squared do cancel out, which is what we want. And then we can finally multiply 124 million times 0.00001 kilometers squared. And this gives us 124 kilometers squared. Here is a nice table that is used to convert English units of area. We have 1 square feet is equivalent to 144 inches squared, or 1/9 of a square yard. And 1 square yard is equivalent to 9 square feet. And 1 square mile is equivalent to 3,097,600 square yards, or 27,878,400 square feet. So it's useful to take a picture of this. You might need it for some homework questions. So here are the land measure units. The English units consist of acre and square mile, and the metric units are hectare and square kilometer. Here is a nice table to look at the conversion units between land measure. For the unit of area, we have 1 R is equivalent to 100 square meters. 1 hectare is equivalent to 100 Rs, or 10,000 square meters, or 1 hectometer squared. 1 kilometer squared is equivalent to 1 millimeter squared. 1 acre is equivalent to 4,840 square yards. 1 square mile is equivalent to 640 acres. Example. Part A. A square field has a side of 400 meters. Find the area of the field in hectares. We have the figure consists of 400 meters by 400 meters. So in order to find the area, we just simply need to multiply these two values together or simply square them. So we have 400 meters squared. That's going to be equivalent to 160,000 meters squared. Part B. A square field has a side of 400 yards. Find the area of the field in acres. We know this is a square field, so this is 400 yards by 400 yards. To find the area in square yards, we'll just square the number. So this is 400 yards squared, and that's going to give us 160,000 square yards in area. But the question wants the area to be in terms of acres. We'll have to multiply 160,000 square yards by our conversion, and for that we'll go to our table. We know that 1 acre is equivalent to 4,840 square yards. So we'll use this for our conversion. I want the yards to be on the bottom, and I want the acres to be on the top. So I know 1 acre is 48,040 yards. So the yards do cancel out, and we have 160,000 divided by 4,840. And this gives us about 33.1 acres. Approximately 33.1 acres. Now we're going to go over the areas of common figures. For the area of a rectangle, it's going to be length times width. And here's an example where the length is 4, the width is 3, so the area is 3 times 4. So we have the area is 12 square units. The area of a parallelogram is just base times the height. Here the base has a length of b and the height has a length of h, so the area is just b times h. You can also view it in a different perspective. If the base is a and the height is g, the area can also be written as ag, and that will be equivalent. The area of a triangle is 1/2 base times height. Here the base is on the bottom and the height is h. Now the reason the area of a triangle is 1/2 base times height is it's because it's half of a parallelogram, and that's where the 1/2 comes from. Remember, the area for a parallelogram is base times height, and since we're only looking at half of the parallelogram or triangle, we're going to have the 1/2 in the front. Let's look at these 3 examples, and I want you to quickly pause the video and try to find the areas on your own. After that, you can observe the answers. Remember, you gotta pause the video, try it on your own. Don't wait for me to do it. Alright, let's try it together. Recall, the area of a parallelogram is base times height. So the problem with this question is there's multiple lengths that are given, and we have to figure out which one is the base. Now the height is always taken along a perpendicular. So I know the height is going to be 8 centimeters, and the base has to be perpendicular to the height. So the base here is going to be the 5 centimeters. So do not use the 10 centimeters. It must be the 5 centimeters because that's taken along a perpendicular. So we know the area is equivalent to the base, which is 5, times the height, which is 8. That gives us 40 centimeters squared. For figure 2, this is a triangle. The base is 10, and the height, again, is always taken along a perpendicular. For the area of a triangle, it's 1/2 base times height. In our case, the base is 10, so we have 1/2 times 10 times the height, which is 4. This gives us an area of 20 square centimeters. For figure 3, this is a triangle again. The base is 2 centimeters and the height is 4 centimeters. Again, the area of a triangle is 1/2 base times height. So the area is 1/2 times 2 times 4. And this is going to give us an area of 4 square centimeters. The area of a kite can be found by relating it to the area of a rectangle. Here is the figure of a kite, and if we were to cut it up and rearrange it, you would actually get a rectangle. Notice that the area of 1 and 2 can be combined together to make a rectangle, and the area of 3 and 4 can also be combined together to make a rectangle. So the area of a kite is given as 1/2 d1 times d2. d1 is the height of the kite, or the length of the kite, and d2 is the width of the kite. The area of a trapezoid is given by 1/2 times the height times the quantity b1 plus b2. Find the areas of each trapezoid. So please pause the video and try these on your own. For the first one, we know the area of a trapezoid is 1/2 times the height times the quantity b1 plus b2. In the first figure, we have b1 is 16 centimeters and b2 is 12 centimeters, and the height is 4 centimeters. So the area is equal to 1/2 times the height, which is 4. We'll multiply that with 16 plus 12. And this gives us an area of 56 square centimeters. Part B. We know the base angles are 45 degrees. That implies that this top angle must also be 45 degrees. So this is a 45, 45, 90-degree triangle for each of the sides. So I know if this has a height of h, this also has to have a length of h, and so does this. So I know the segment AE and the segment FD must be equal to a length of h. Since we have the segment BC and EF forms a rectangle, this must be a length of 2. And I know the segment from A to D is 8 centimeters, so we can put h plus 2 has to be equal to 8 centimeters. H plus h gives us 2h plus 2 equals 8, and I can subtract the 2 to both sides, and so 2h equals 6, and h must be equal to 3. So we know h is 3 centimeters. We know the formula again is 1/2 height times b1 plus b2. So we'll do the work up here. We have 1/2 times the height, which is 3, and we'll take the base here, which is 8, and we'll add that to 2. And this gives us an area of 15 square centimeters. The area of a regular polygon is calculated by taking the altitude, which is essentially the height of this small triangle, to the base of one of the sides. So the altitude here is the height from the center to the side of our polygon, and S is the distance of one of the sides of that polygon. So the area is equal to 1/2 times the altitude times n, which is the number of sides of the polygon, and we'll multiply that by S, which is a segment of the sides. And that is equal to 1/2 times the altitude times the perimeter. The area of a circle can be calculated in the same fashion, and if you look at it for infinitely small triangles, we have the area of a circle is equivalent to pi r squared. The area of a sector is calculated by the central angle theta and this radius. So we have the area is equivalent to our angle theta, which is our central angle, divided by 360 degrees, times pi r squared. So this is the area of a circular sector if we're given the angle in degrees.